Okay, welcome back, ladies and gentlemen. So here is a review problem because the final is coming. And so we've got this review problem up on the board here, and to give you a minute to solve it, I replaced the 8 with a 2 to the third because I know you'd eventually figure that out. And we've got it down to, got to multiply both sides by 7, and so that makes it W equals all that, and then see if you can figure out what to do. I'm going to pause for a second while you figure that out. So, who figured out that you could move this 3? How many of you figured that out? Do you remember that? If you didn't remember that, it would be a very difficult question. Where can that 3 go? It goes up as a exponent on that one. That is called the power rule. There's a lot of little rules and logs. This is one of the reasons that you'll want to review. We do a practice before the final. Do you remember last semester where there was a take-home portion of the final and it was therefore takes some of the pressure off the final itself? Because you can kind of lock in some, and it's also a way to review for the final. Same thing. You're going to have that this time, so you can lock in like a third of your final score will already be done before you get there. It's not going to be an easy set of problems, but then again, it helps you prepare for the final too. So, all right, and you can work with other people on that, which should help. All right, so anyway, in the midst of your reviewing, hopefully you'll remember that this can move up here, and that's the power rule from in front of a log. You can go up and be the power on the, called the argument there, and that's really 27. And why does that matter? Because when you have a setup like this where the bases are the same, do you remember that if the bases are the same, then that's the answer? I'm going to give you another one off to the side. If I had 3, log base 3 of 9, the answer would be 9. Okay, if these two are the same, then that's the answer. The bases are the same. See, this is a base. It has an exponent on it, and that's the base of the log. When those bases are the same, the answer's already there, and it's a 9. So this one isn't 9. It's 3 to the third, which is what? You know what 3 to the third is? 27. So then I have a 7 times all this part was 27. So it's 7 times 27 equals W. Tough, but not impossible. The key leap was you had to know to change this 8 into 2 to the third. Then you had to know that this would get multiplied, because you know that about power to a power, is that they multiply. And then you had to know to move that 3 up as a power on the argument. How many of you actually got to that point where you figured out it was 7 times 27? All right, that was a stretch, but it caused me to give you a chance to think about how you have to remember some stuff from previous chapters for this final. Logs is one of them. All right. Next, I want to just show you something that's a cool application of addition of vectors. I don't know if you know this. It's just about that this is something that would happen. If I connect a rope to 2 things, like I'll keep it simple. In this classroom, let's say I have a rope connected to this desk and this desk. If that rope is really tight, can you picture that when I pull on the rope, it'll move the objects? Right? I mean, if the rope's tight between them and I pull on that, it's going to move the objects. Well, these are easy to move, right? Because they're just like, they're 2 desks that slide easily on the floor. Did you know that if you connected a rope to 2 cars and you got it nice and tight and you pulled in the middle of it, if the rope was fairly long, if you pulled in the middle of it, you could actually budge one of the cars, make it move? Like it would drag the car's wheel on the parking lot, and it would actually, you could move a car with this. Why? Because of the power of addition of vectors. Okay? So this would take me a long time to explain the details of it. I wanted you to know that this is a thing, and I may talk about it more on a day when I have more time, but I have a lot of things to teach you today. But this is an example of vectors. Where is the vector involved? The vector is a distance, and we moved this rope towards yourself as you're pulling it towards yourself, okay? And that is the vector. You're applying a force in this direction, and the distance here is what magnifies it. Have you heard that saying, give me a lever long enough and I can move the earth? It uses that same principle. Archimedes, I think, is the one who said that. Basically, if you have a really long pry bar, you can get a lot of force on something if the pry bar is really long and you push down on it? All right. Again, these are like hands-on things that we don't talk about in math that often, but I thought I'd show you this. That's actually an application of addition of vectors. All right. I want to get to the main thing for today, which is this slide right here. I need to make sure you understand this. All right. So this vector here is that A, this A is being described here. A is the vector, and remember, a vector isn't just a point. Before I kept on saying over and over again, this is just a point. Vector is not just a point, it's the whole arrow in between, okay? And that length is important, and that's its magnitude, right? And so if I wanted to write this vector in position vector form, it would look like this with an I and a J. Kind of got you started on understanding that yesterday. So let's see what this one would actually be. This one would actually be how far in this direction. That's considered the I direction. Again, I wish they hadn't used I because, you know, I usually stands for imaginary numbers. But it goes 1, 2, 3, 4, 5 in the I direction. And then it goes up 3 in the J direction. Okay, so this guy's position vector would be that it is 3 in the, or sorry, I did it wrong, backwards. X is 5 in that direction and 3 in that direction. Now, there's two things here. There's the spot at the end. We can give a name to a spot, but that's a position. That's a spot. There's a position vector, and then there's the vector itself. So when I say 3, 5, you can think of a spot or the vector that goes to that spot. All right. This is a spot. That is a unit vector. It's going 1 in the direction of X and 0 in the direction of Y. That's like a little tiny 1 inch, you could say, if this is in inches, long vector in the X direction. This J is a little 1 block long, 1 inch long vector in the Y direction. So really what this is doing is this is 5 sets of little unit vectors, and this is 3 sets of little unit vectors. Now, if you didn't understand all of that, but you could still put this together and say, let's say I go out 3 in this direction and up 2 in that direction, that this spot right here, that spot, could be called a position of -3, 2. Ooh, what are you writing it that way for? Because that's how we write vectors. We don't write them as -3, 2. That's a position vector. That's saying that's its position. It's at over 3 to the left and then up 2. Now there's position vectors, and then there's like equations that use these vectors. But for right now, if I just say 3, -2 is that spot right there, do you get that that went in the I and the J directions? And it went -3, it went 3 to the left, and then it went up 2. Okay. Now, what if I wanted to make that thing twice as long? If I wanted to make that thing twice as long, if I go like that and I put a 2 in front of it, what does that do? That's going to make my position vector move to, simple as this. You multiply that and that. -3 times 2 makes -6, comma 2. I'm going to go over 6. And then 2 times 2 makes 4, so I go up 4. And it just doubled my vector length. Or did it? Did it actually double the vector length, or is the vector actually longer than that now? Let's see what the vector was here. It was square root of 9 and 4 makes 13. Do you think that this just got twice as long? Or do you think it got even longer than that? When you double all the sides, will it actually double the hypotenuse also? Or will it more than double the hypotenuse? This total length here, nobody's answering, but I think some of you know. Can you just double the sides and will the hypotenuse just double too? All right, I'll give you this question. 3, 4, 5 triangle. Say I double the 3 and the 4. Will the 5 get doubled? Will it? It's amazing how you guys are really not sure. If this becomes 6 and this becomes 8, doesn't that become 10? It does. Okay. But I know there's things in math that are like that where, okay, you double the size, they double the radius on a circle, and the circle doesn't just get twice as big. You know what I mean? It's more than twice as big. But in a triangle, yeah, 3, 4, 5 can be doubled to be a 6, 8, 10. All right, so that means if I had this vector, I'm going to call it R, and this vector was at 6, 8. What are you saying, Mr. Server? Is that a dot? Or is that a vector? Well, it depends. There's something called a position vector, which is just the position 6, 8, versus a vector that goes from 0, 0 to that position. What I was trying to get across was over 6 up 8. Let's say there's a dot there. That you can call that a position, and that's the position vector. Or we can say that we have a vector that goes to that position. And now the vector is the line that goes there to this position of 6, 8. And how long is it? Is it 6 or is it 8? No. And you'd have to figure that out. So do you get, if I start giving you vectors like this, that's not their magnitude? Their magnitude isn't 6 or 8? Would you figure out the magnitude of the vector that would go to this position? I'm going to pause for a second while you figure out the magnitude of that vector. It's not 6 and it's not 8. It's not 10. All right, I'm going to pause for a second while you figure out the magnitude of that vector. Okay, so I hope you figured out that when I said magnitude, I was talking about the length of that. And I need to unfreeze my board here just a second. And so this is 6, and this is 8, and this is the square root of 6 squared, 36, plus 8 squared, 64, square root of 100, and it is 10. I'm sorry, I said it wasn't 10, but it is 10. I thought it was something else. My bad. Okay. All right, so that one is my magnitude. So the magnitude, don't just, I hate the 6, 8, 10 because it seems like you just add 2, and add 2 to get the answer. You know what I mean? 6, 8, and what's coming next? 10. That's not how we get this at all. But the magnitude of this one was 10. All right. Now we got to talk about having two vectors and adding them together and what that looks like on a graph. Find this slide. Now, this part is going to bother some of you because, and I understand why, because remember me saying before that if you have a vector like this one here that is over here, and if I were to clone it, make another one, that's the same vector. They're the same. And you're thinking to yourself, but they're in a different place. They're the same. They're equal. So if I move it over here also, it's still equal, isn't it? Okay, so that A vector that I just moved over, here, let's get B out of here for a second. But you get B is still the same as it was before. I just moved it. It's still got the same direction, still got the same magnitude, so it's the same. All right, so anyway, I just moved A over here. So now I put A over here. Why do you think it's nicer over there? It's easier to tell what it is. What is that vector? A is, this is in column vector form, for 3. Do you get what I just did there? Over 4, up 3. Do you get that even though A started over here, it was 4, 3? Because if I move it so its tail end is at the origin, it's just easier to tell that it's 4, 3. Could I have figured it out from here? Yeah, I could have figured it out. I could have just gone over and up and said, oh, it's 4, 3. All right. Given what I just said, what would you recommend to figure out, what should I do to figure out what B is, actually? Remember, we just figured out A was 4, 3. That's writing it as a column vector. By the way, to write it as a position vector, all you got to do is say with the I and the K. So this would be 4I plus 3J. Oh, wait a minute. K. I usually use J. J. Okay. How about this B? What's it? Could you grab it and move it over so that it is sitting right here? Yes. But do you get that that's actually kind of a crutch? Am I going to just count to the left and count up, and therefore couldn't I just do that from here and say this is, oops, don't move it, 1, 2, 3, 4, 5 over, and then 1, 2, 3, 4, 5 up, and therefore what is B in column vector form? -5, comma, 5, or -5 over 5. Now here's my challenge for you. How do you add A plus B? Well, I could do that pretty easy. I can take A, I can even move it, remember? I can move it over here if I want to. And then I can take B and I can move it over here if I want to. And then I can figure out the resultant by looking at this. But that probably wasn't the logical place to move these two. What would the logical place been to have moved them? Where do you think I should start? Because everything always starts best there. At the origin. So I'm going to move this over to the origin. And I'm going to move this. But now this is purposely off the screen. So that we can't just say, oh, the answer is that dot that we can't see up there. What I want you to figure out is what could you have done with these two things that would have told you the answer. The answer is a vector that goes to that dot. So like the answer might be 1, 8 or something, wherever that tip ends up. What could you have done to these numbers to make this answer vector? And again, this is not the right answer vector. You got to figure out what that is. I'm asking you to learn how to add vectors by moving these around and figuring out what you must have to do to the numbers in the vectors. I'm going to pause while you figure that out. Your final answer would be, Mr. Server, the answer is the resultant, which goes like this, and its vector name would be, 1, 8, or whatever it is. All right, I'm going to pause while you figure that one out. Okay, we're getting low on time, so I need to get going here. So, did you guys figure out it was actually at -1, 8? Raise your hand if you figured that out. All right. So then, if it's -1, 8, then what could we have done in the first place? Couldn't we have just added this part and this part? What's 4 and -5 make? -1. Couldn't we have then just added the 3 and the 5 and gotten the 8? All right, so then I ask you, what if we had these two vectors, 2, 1, plus 8, negative 4? Couldn't this, can you picture what that would look like as a vector? It goes over 2 and up 1 to get there. And remember, it could be right here at the origin where you go over 2 and up 1, or this vector could be anywhere. And if you want to know what it is, you just move it back here and realize, oh, it's going over 2 and up 1. So that's the vector 2, 1. And then I'm adding the vector 8, negative 4, which again goes up 8 to the right and down 4, and that's like this. That vector, which again could have started anywhere, and I could have moved it here and then saw, oh yeah, it's going 8 to the right and down 4. And what if I want to add them together? Well, yeah, you can slide your vectors around, but you could have just, what? Added the top 2 and you get what? 10. Add the bottom 2 and you get what? Does this vector, that the resultant, look like it might have gone over 10 and down 3? Does that seem possible to you? All right. So that's all you got to do is add the top parts, add bottom parts. All right. So now I want to get back to a piece of graph paper. Actually, I should use graph paper here. There we go. Okay. And now I'm going to give you this little vector right here. And this little vector right here. And I'm going to say this one's A, and the green one's B. And my question is, what's the name of A? What's the name of B? And then what do you get if you add A plus B? Do them in column vector form. We almost always use column vectors. The thing in parentheses, you know, like this, that kind of thing. All right, figure out what the name of each vector is and then try to add them together. I'm going to pause while you try that. Okay, for your A vector, did you get 2, 2? Raise your hand if you had 2, 2 for your A vector, okay? For your B vector, did you get 1, negative 1? Raise your hand if you got 1, negative 1. All right, if you didn't get that, here's how you could have gotten it. If I move it up here, do you get now I can see that it goes 1 to the right and down 1? That's how I get my 1, negative 1. Okay, now if I wanted to add them, if it was this simple, I could always just grab this, move it up, and say tip to tail. And then my answer must be this little red vector. You get, I could have got that, though, by just adding these, and I would get 3 over negative 1. And, but, wait a minute, sorry, positive 1. There you go. Now, here's the extension. What do you think happens if I double the smaller one here? I put a 2 in front. It's as simple as you would think. What do you think the top part would be? 2 plus 2 times 1 be 4. What do you think the bottom part would be? 2 plus 2 times negative 1. That makes negative 2. 2 plus negative 2 is 0. And what is 4, 0? It's a vector that would go 2 to the right, or no, sorry, 4 to the right and straight down. Do you get if I would have doubled? Actually, I shouldn't use green for this. Second, do you get if I would have doubled the little green vector and then subtracted? Do you get, or sorry, added? Then it would have been there, and 4, 0 is there. All right, so you should have learned a couple things today. If I give you a vector that looks like this, you should be able to say, oh, Mr. Server, that is the vector 3 to the right and up 2. 3, 2. You could get that by sliding it here if you have to. See, it goes over 3 and up 2. Okay? But then if I want to add this little vector to it, you got to figure out what vector that is. And, oh, I'm going to say that vector is 1, negative 1. And if I just simply want to add them, you just simply add the x's and you add the y's. What if I wanted to subtract them? It's as simple as you would think. If you're subtracting it, you go 3 minus 1 and 2 minus negative 1, which would mean 2 plus 1. What if I wanted to double this one? It's as simple as you would think. If you double the sides on a triangle, you're also doubling the hypotenuse, right? So 2 times 3 is 6. 4 makes this guy double length. All right. There. Hopefully, you learned everything that you needed to know for today. So now we're going to go to the assignment day 3 and show you a few problems that are like that. Finally, today we've gotten into the meat of where you're going to get tested on is these column vectors like this. We're just on day 1 of it, but at least they kind of look like the test questions are going to look. If you see this, I see this. 1, 7, -1. You get what I just did there? And what's different about this? It's got 3 dimensions. X, Y, and Z. It's like a vector that is going 1 to the right, up 7, and then what's this -1? That's going away from you, like into the smartboard. Do you get the whole 3-dimensional idea? All right, we'll talk more about how that works, but don't freak out just because there's 3 numbers here. That's X, Y, and the third one is Z. So I'm going to see if I can get across that one more time to you. Imagine for a moment that I had a vector that's in 3D, and so that it doesn't just have to lay flat on the smartboard. It can come out towards you. So imagine this one goes over 4, up 4, but then comes out at, actually this still looks more like 3. So I'm going to say that it's over here. There. It goes over 4, up 3, but then it comes, I have to do this kind of like this. It comes out towards you. It comes straight towards you, 1. Then I'm holding my marker on the board here. It's like this. It's coming over, up, but then it doesn't just lay flat. It comes out 1. That makes it 3-dimensional. All right. Pausing for a second. So your assignment is to do all the problems on page 1 and 2 of our smartboard slides. And that's all I got for you for today.